This is tutorial 1, question 3. And here we have a single reservoir being discharged into a single pipe that then splits into two pipes which discharge into the atmosphere. Reading the problem, it goes like this. Water is drawn from a reservoir tank whose surface level is 20 meters above the ground through a 125 diameter pipe, has a length of 40 meters, coefficient of friction of 0.04. The line then splits into two parallel branches that discharges at ground level into atmosphere. The first branch having a dimensions of 50 millimeters diameter and coefficient of friction 0.024, a length of 18 meters. The second branch have a diameter of 75 millimeters, friction coefficient of 0.024 and a length of 24 meters. They give you the formula to use. Calculate using friction losses and velocity head only the discharge through line 1, the discharge through line 2 and line 3. Alright, so the difference with this problem compared to the previous two we've done is that you're discharging to the atmosphere. So therefore, as I said in my note at the top right, that we have to include the velocity head at the exit of the pipes in our Bernoulli equation, as the fluid at the exit still has kinetic energy leaving the pipe. Alright, so let's have a look at calculating the head losses in the pipes themselves, similar to what we've done before. So head loss due to friction in pipe 1 is equal to F LQ squared over 12,1 D to the power of 5. Substituting, we get 0.04 times 40 Q1 squared over 12,01 and 0.125 is the diameter to the power of 5, which then ends up giving us 4,365 Q1 squared. Head loss due to friction in pipe 2 is 0.024 times 18 Q2 squared, and we divide that by 12.01, 0.05 to the power of 5, and that gives us 115,104 Q2 squared. Head loss due to friction in the third pipeline, 0.024 times 24 meters long, Q2 squared, and 12.01, 0.075 to the power of 5, which gives us 20210 Q3 squared. Now we have to determine the head loss, the velocity head at the exit of the pipe in terms of discharge. So we have the velocity head at the exit of the pipe, number 2. We know that's V squared over 2G. We know that Q is equal to VA, or V is equal to Q over A. So HV2 is therefore Q2 over A2 squared divided by 2G, or Q2 squared over pi over 4 times 0.05 squared, and that is all squared, times 2 times 9.81, giving us HE2 13,220 Q2 squared. So we now have the velocity head in terms of discharge as well. Alright, let's do the same for the velocity head exiting the third pipeline. That is Q3 squared over pi over 4.075 squared times 2 times 9.81, and that would be HP2 2611 Q3 squared. Alright, now we can apply our Bernoulli equation. From A to B. So the difference in height is 20 meters. HF1 plus HF2 plus HV2. The velocity head at exit of part 2. So therefore 20 is equal to 4,365 Q1 squared plus 115,104 Q2 squared plus 13,220 Q2 squared. In terms of Q2, we get this equation, 20 minus 4,365 Q1 squared, and that's all divided by 128324. That's our first equation. And now we have to apply Bernoulli from A to C. Still 20 meters height difference. HF1 friction loss in pipe 1, HF3 plus HV3, the velocity head at exit of pipe 3. Substituting, 20 is equal to 4,365 Q1 squared plus 20210 Q3 squared plus 2611 Q3 squared. In terms of Q3, we can simplify this to be 20 minus 4,365 Q1 squared divided by 22821 that will be equation number 2. So for continuity of flow, Q1 is equal to Q2 plus Q3, and that is our third equation. Substitute one and 2 in 3 Q1 is equal to the square root of 20 minus 4, 3, 6, 5 Q1 squared over 1, 2, 8, 3, 2, 4 plus Q3 is equal to the square root of 20 minus 4, 3, 6, 5 Q1 squared. Divide that by 2, 2, 8, 2, 1. Using successive approximation or your calculator, you can figure out what Q1 is, and that will give you a result of 0.03579 cubic meters per second. From equation number 1, Q2 is 0.0106 cubic meters per second, and from equation 2, Q3 will be 0.0251 cubic meters per second. And that is the end of